Black holes, shoes. Okay, you read the title, you know what you've gotten yourself into, but you may well be wondering why. You see, recently I have been reading the Hitchhiker's Guide to the Galaxy books, and in the books there is a rather sad economical phenomenon called the shoe event horizon. What happens is, if you're in a place that is not so good, you feel sad and down, so you look down at your shoes. Since that becomes the only thing you see, you go and buy a new pair of shoes to cheer yourself up. Everyone does this, because everyone is sad, and so the demand for shoes goes up, and more shoe shops pop up, because companies are making an investment by making more shoes. Eventually, all shops are shoe shops, and that's not good, because people need food shops and stuff as well. However, it becomes economically impossible to make any shop other than a shoe shop, because the economy is at a shoe tipping point, or event horizon, and past the point of no return. So everyone dies and drowns in shoes because they were sad. And that is why mental health is no joke. Anyway, I was reading it and remembered that because of the Schwarzschild equation, which I'll explain in a bit, if you keep throwing matter at a single spot, eventually that matter will collapse and form a black hole. And I thought, hey, assuming that these guys will keep being sad and keep drowning in shoes, at one point those shoes could form an actual event horizon. How many shoes would that take? So, naturally, I decided to calculate it. And here we are. But before we calculate it, let's talk about black holes and the principle that's making this possible. Black holes are points of space where gravity has such a strong pull, not even light can escape them. That's why they're called black holes, because you can't see them as no light is reflected or even able to leave, if it reaches the event horizon. So there's no way for photons of light to reach our eyes. Therefore, they're invisible. We can only really see objects interacting with them, for example stars orbiting them. The event horizon of the black hole, so the point at which the escape velocity is so high that not even light, which is the fastest thing in the universe, can escape, depends on the mass of the given black hole. But why is gravity so strong in black holes? Well, gravity depends on an object's mass, and black holes are usually quite massive, because that way it's easier for whatever object it was before to collapse under its own gravity and form a black hole. However, there are many objects in the universe that are very massive that light can escape from, like stars that are really, really big. So what distinguishes massive objects from black holes? Well, black holes are massive for their volume. This means that there's a lot of mass in a certain small space, i.e. black holes are very, very dense. Infinitely dense, in fact. So there's a lot of gravity in a single space, to put it simply. But how do black holes come about? Or rather, how does one make a black hole? Black holes can be made in one of two ways. One of them is to squish something so much that it becomes so dense it reaches the tipping point and forms a black hole. For example, when very, very massive stars get to the point where they can no longer do nuclear fusion to counteract their gravity, because they have reached extremely heavy elements, they collapse under their own gravity. This causes the matter to be squeezed into an extremely small point, and if the star is big enough, a black hole is formed. Theoretically, you could do this with anything. A tennis ball, the Earth, as long as the matter is packed close enough together. But it would be a very, very tiny black hole. To give you a frame of reference, a black hole of the same mass as the Sun, which has the mass of around 2 × 10 to the power of 30 kilograms, and a diameter of around 1.4 million kilometers, would have a diameter of around 6 kilometers. 6. My college is farther than that. The other way is to keep throwing matter at a single point until that collapses and forms a black hole. But how does this work? Well, before we get into that, let's have a look at how the idea of a Schwarzschild radius came about, and how we can calculate it. This is Newton's Law of Gravitation. The g is the gravitational constant. Big M is the mass of object 1, and little m is the mass of object 2. The r is the distance between the centers of their masses. What this says is that the bigger the masses, and the smaller the distance between them, the stronger the gravitational pull of those objects. Now, this means that, at one point, either if you keep adding mass or lowering the radius, the pull will be so strong that for one object to leave the other, it would have to move faster than the speed of light, though that's not possible because of general relativity. But that's what happens with black holes. Not even light can escape them because their gravitational field is so strong that the escape velocity is higher than the speed of light. This must mean that there is a point where an object can get small enough that while keeping the same mass, its escape velocity will be greater than the speed of light. Therefore, it becomes a black hole. So let's try to figure out how to get to that. This is the equation for gravitational potential. Potential is the ratio of the energy that the given field is either giving or you have to give to the field per unit of whatever potential we're talking about, to remove it from that field. So gravitational potential is the energy divided by mass, because that's its property. It'll only ever be the energy that we supply, as there is no such thing as negative gravity, so there will be a minus at the front because the field will have to take the energy from us. Gravitational potential is the negative of g times the mass of the object causing the field divided by the radius. The type of energy you'd need to move an object in the field is kinetic energy. So if we stick the formula for it into the gravitational potential equation, we get that a half velocity squared is equal to the potential. We can put a minus sign there because we're going to have to put the energy in. Therefore, half velocity squared is equal to g times the mass of the object causing the field divided by the radius. We're talking about an instance where v is equal to the speed of light, as that will be the cutoff escape velocity. So v is equal to c. Therefore, the radius is equal to 2 times the g and the mass divided by the speed of light squared. Boom! We did it! We have an equation for how big an object has to be for its escape velocity to be the speed of light. This is called the Schwarzschild radius equation, and it was derived by Carl Schwarzschild in 1916. As you can see, the radius of the event horizon of a black hole is directly proportional to its mass. However, if we were to use this equation now, because, we're trying to find out how to make a black hole out of shoes, we would get the size we'd have to squash the shoe to get it to become a black hole. That would be assuming we are modeling it as a sphere, and the mass of the average shoe is around 1 kilogram. The shoe would have a radius of around 1.48 times 10 to the power of minus 27 to become a black hole. Mind you, the radius of the average atom is around 0.1 micrometers, or 1 times 10 to the power of minus 10. Yeah, I don't think that is feasible. Well, none of this is feasible really, but that is definitely not feasible. So we'll have to find a different approach. What we want is for the radius of the object we want to make into a black hole to be equal to its Schwarzschild radius. This is the equation for the radius given the volume. Now, the Schwarzschild radius will, in most cases, be much smaller than the radius of the actual object, unless that object is a black hole or about to become one. However, if we look for the core correlation between the mass and the radii, because all the other numbers will essentially be constants, the radius is proportional to the cube root of the mass, and the Schwarzschild radius is just proportional to the mass. If we say that the mass is equal to x, for example, and draw the two equations as graphs, I put x over 10 here because it's just easier to see, but it will work with x on its own. As you can see, the blue, which represents the Schwarzschild radius, and red, which represents the normal radius, will eventually meet, even if I change the numbers, though sometimes the intersection is a bit far for me to show, but you get the idea. Okay, but what does it mean? Well, it means that as we increase the radius, we will also increase the Schwarzschild radius. However, because the Schwarzschild radius grows faster than the radius can, eventually the object will collapse into a black hole. What we need to do is keep throwing stuff at the same point, so we increase its radius to make its Schwarzschild radius catch up. So all we should need to do is set the radii equations equal to each other, which will give us the point of intersection, where the actual radius of the object will be equal to its Schwarzschild radius, sub in the numbers, and find the mass of the massive shoe pile that will collapse into a black hole. Doesn't sound too bad, right? So now we just need to find the numbers. I don't have a working weighing scale, so I can't measure the mass of the shoe myself, but Google tells me that the average mass of a shoe is around 1 kilogram. What I can measure is the volume of one of my shoes though, which I did by submerging the shoe in a volume of water, and the volume that spilt out was the same as the volume of the shoe, which turned out to be around 240 milliliters. Then we can calculate the density. Now all we need to do is sub in the numbers, do a bit of rearranging, and bam! This is the mass that the massive shoe pile will have for it to turn into a black hole. And because we said that the average mass of a shoe is 1 kilogram, that is also the number of shoes we need. Around 1.33 times 10 to the power of 38. For comparison, the mass of the Earth is around 6 times 10 to the power of 24. So it's 4 orders of magnitude bigger. Just to show you just how big of a number this is, let's sub in the mass we got back into the Schwarzschild equation and see what the radius of the shoe black hole thing would be. Since we set it to the actual radius, the radii will be equal. So the black hole's radius would be 2.95 times 10 to the power of 21. Now the radius of the Milky Way is 5 times 10 to the power of 20. It would be bigger than our own galaxy, by a whole order of magnitude. That's humongous. The only thing we have left to do now is to make it. Anyone know where we can get the money for this? Like, are there any grants or funds or any billionaires in the audience? If there are sub-billionaires, you guys want to make a black hole out of shoes? Give me a sec, might need to rob a few banks.